So far, what have we, so as I said, the first question we're going to answer in this course is, what is an integral? So far we've talked about integral in a couple different ways. We've talked about an integral as if you know a derivative, what's the original function? We've talked about it in terms of you can represent it using a slope field. We've talked about the integral as it's the equivalent of finding the area under a curve, and of course, and that means signed area. So above is positive and below the x-axis is negative. Briefly, we mentioned you can use it to think about real world problems. So I want to talk about some of those applications right now. Okay. So, what is the derivative of distance? Ooh, it's velocity. Okay, so this is important to understand. So if you're measuring distance, derivative is the same as the rate. So if you're measuring things in distance, then what's the rate relative to distance? What do you call that? That's velocity. Okay. Now, if you're measuring the rate of change of velocity, the derivative of velocity, what is that? That's, okay, now we're awake. Now, yes, it's acceleration. Okay. So now that we know, now we remember that there's a relationship, start with distance, velocity, acceleration. So by the same token, if I gave you the acceleration, how would you get to velocity? Take the integral, exactly. And that's the kind of problem we're going to start talking about right now. First, let me just make some comments. Okay. So we also refer to distance as position or displacement. So a small technical comment about this. Technically speaking, position or displacement is different from distance. So I'll give you an example of what I mean by that. If my pen goes here and then goes back, have I traveled any distance? Yes. However, what is my displacement? My displacement is 0. Okay. So sometimes I'm probably going to be sloppy and I'll say distance when what I really mean is displacement. So for our purposes, we're only going to talk about position and displacement. You could talk about distance, and the way you do that mathematically is just by taking the absolute value. So that positive changes and negative changes all count instead of canceling each other out. All right. But for our purposes, we're generally just going to skip that. Does that make sense? Okay. So that being said, moving on. So we're going to call this function for distance, position, displacement, I'm going to call it p of x. Why don't I call it d of x? Well, we're already using the letter d for something really important, the derivative. And we're talking about derivatives all the time, so we want d to be reserved. Okay. So let's look at a problem now. So at time t, the velocity is 2t. What is the position function? So what is it?
T squared plus c.
Yeah. Because how do you find it? Take the antiderivative, exactly. Because we know that velocity is really just p prime, and we're trying to find p. So p is the antiderivative of p prime dt. So that's the antiderivative of 2t dt. It's just t squared plus c. So what if I wanted not just the general position function, but the full complete position function? What do we need here? We need an initial condition. So there you go. At time t equals 1, the position is 2. Let's say 1 second and 2 meters. Okay? Then what's the position function? You plug it in and you solve for what c is. C is 1. Therefore, we write down our final answer. P of t is t squared plus 1. Okay. So this is a case where instead of just asking about p prime and p, I can actually ask in terms of a real-world context, in this case, position and velocity. All right, let's kick it up a notch. So the acceleration of a free-falling object is 9.8. So who actually knew the value of the acceleration? It's called the acceleration due to gravity. Okay. So a fair number of people. This is one of the first things you learn in physics. Now there's actually two different numbers for it. So one of them is 9.8, and that's meters per second squared. And I'm always going to, well, the other option is to say 32 feet per second squared. I'm always going to use metric units because metric units actually make sense. American units, not so much. As we'll see in another example coming up. Okay. So there you go. So once we know that, and we're referred to position as p, velocity as v, and acceleration as a, because we're very clever. Okay. What's the velocity at time t? So what do you have to do? Right. So what do you have to do? You have to integrate, exactly. So v prime is a. So here so previously we just did it the plus c way. Here I'm going to do it the fancy way using the full fundamental theorem of calculus statement. So what we know is that v of t minus v of 0 equals the integral from 0 to t of v prime of x dx. And of course, v prime is just a. So a was 9.8. So when you take the antiderivative, 9.8x. And now you evaluate it from 0 to t. So you just get this. So now I did something very specific. I didn't use the plus c method because using this formulation we can see exactly what the plus c is. What is the plus c? It's the velocity at 0. So that plus c isn't just a dangling constant, it has a very specific meaning in this physical context, which you get to see if you use the fundamental theorem of calculus, which is why I love it. Okay. There I typed what I just said. Okay. And those of you who've taken physics, you're very familiar with this notation. Instead of writing v of 0, physicists like to write v0. It means the exact same thing. It's just notation and how people choose to write stuff down. Okay. So let's go further. What is the distance or position at time t? What do we have to do now? Integrate again. Okay. So I said position was going to be p, so let me stick to that. Okay. Right? Yeah. Okay. Okay. So once again, I'm going to use the fundamental theorem of calculus. P of t minus p of 0 is just the integral from 0 to t of p prime. But we know what p prime is because it's v, and we just found v. The v function was this. So you take the antiderivative of that. So the antiderivative of 9.8x, 9.8x squared over 2, which is just 4.9x squared. And the antiderivative of v0, v0 is just a constant, so it's v0 times x. And now we evaluate this from 0 to t. So you plug that in, and you get that minus that. You work that all out, and you get this. 4.9 t squared plus v0 t. Rest just goes to 0. But now we can actually solve for the position function. P of t equals this. So once again, we got a constant popping up, but that constant actually means something. What does the constant mean in this case? It's the distance or the position when time equals 0. Or in physics, what you would call your initial position. So we can actually use this to solve some problems. So, if an object has an initial position of 3 meters and an initial velocity of 4 meters per second, what position is it at when t equals 2 seconds? So, now the long way to do this problem is just to start from the fact where we know that a equals 9.8 and then to solve it out. But we just did all the solving out. So what do we do now? Just plug it in. So what in notation, we're trying to find position when t equals 2. What is that in notation? Position when t is 2 seconds. That's just p of 2. So p of 2 equals p0 plus v0 t plus 4.9 t squared. Now I'm going to plug in the 2. So actually, let me be precise. That's not p of 2. That's p of t. And now we're going to plug in 2. So p of 2 equals, well, what was p0? P0, initial position, 3 meters. Plus v0 was 4 times t, which is 2, plus 4.9 times 2 squared. And now we just got to do some arithmetic. So arithmetic, that's 9.6 times 9.6. Okay. So if I did this right in my head, that's 30.6. Someone can check me. 30.6. Okay. Now, by the way, 30.6 what? Bananas? Yeah.
If you do in physics, all the units problem.
Right. Also, what are we measuring? We're measuring distance or position, which in this problem is meters. Okay. So, an important comment on this. When you do context problems, I encourage and basically require that you write the units down. Because otherwise, you're not answering the question. What position is it at when t equals 2 seconds? 30.6. 30.6 what? There's actually a very famous story from, I want to say something about 10 years ago, where there was, NASA sent up a rocket ship, and there was some kind of problem, and there were these technical problems, and like the foam came off, or something actually stopped working, and they had to, they actually didn't launch it, they had to cancel the launch because something was coming apart. And the NASA scientists spent like a month or 2 trying to figure out what went wrong. And you know what went wrong? American engineers were collaborating with British engineers. And the British engineers had done their calculation in metric units, and the American engineers had done their calculations in American units. And they forgot to tell each other.
Wow.
Yeah.
The Americans were wrong.
So write your units down. Because you don't want your rocket ship to explode.
It would be so bizarre because you learn physics in pretty much everywhere in SI units,
Yeah,
even in America.
The metric is international.
And that's why we can't believe it happened. So let's solve that problem right here, right now. Write your units down. Otherwise, I'm going to write down 30.6 what? Bananas?
Can we,
Okay.
when we solve it, can we use physics format like write even because it's easier when we consolidate?
Yeah. Whatever notation format you want to use, as long as it's correct, use it. Okay. I'll know it. Don't worry about it.
Sorry. You skipped one step, right? Like instead of putting 9.8 divided by 2, you go straight 4.9?
Oh, I simplified before. I simplified it because 9.8 over 2 is 4.9. So I'd already simplified it. Yeah. But yeah. Okay. All right. Not sure why that's there. Okay. Oh, wait a second. Okay. All right. So I've said this before. It bears repeating because what we're dealing with now. Differential equations, such as what we're doing right now, are very, very important in math, in physics, in chemistry, in biology, in sociology, anything that remotely claims to be a science. Differential equations are used somewhere. The reason for that is a lot of times what you know about a situation, you can describe. You know it in terms of the rate of change in a situation. So, for example, in a kinetic situation, the information you have might be about the velocity. Let's see. Anyone who's, dealt with oscillators, you're actually making a second derivative statement, is your initial statement. That's a little bit of advanced physics. So anyway, what I want to do right now is I want to look at a bunch of applications. So the first one we looked at was the most basic one of all. It's just from physics, the idea of motion, velocity. Next one, economics. So the first thing we're going to learn to do is how to maximize, maximize our profit and make some money. Okay. So first we're going to look at cost functions. So cost function is what it sounds like. It's simply the function that describes your cost based on the number of units that your factory makes. Imagine you're a factory making stuff. Okay. So the derivative of the cost function, in economics that's known as the marginal cost, so it's called MC, but we're mathematicians, so we're going to write it as C prime. So we know that that's $28 per item. So C prime is 28. Suppose making no items costs $8,000. So, and that might be your cost for rent or some kind of overhead or whatever. So what is the total cost function C of x? So what do we do?
Take the integration of $28 per item.
Right.
With the plus 8.
We want C, we know C prime. So what do we do? Take the integral. So C prime is 28. So the antiderivative is just 28x. Now, of course, plus C. Here I wrote K, I don't know. Oh, why did I write K instead of C? We're already using C. So you got to be careful about those notation things. Okay. So 28x plus K is your cost function. But we're not done. We have an initial condition.
8,002.
So you plug in zeros, you get 8,000. That tells you that K is 8,000 when you solve it. Okay, so now we write down our cost function. It's 8,000 plus 28x. Okay, now what's the cost of 120 items? What do? Just plug it in to C of x. And you get $11,360. Because we measure money in dollars. That's how we roll. Okay. Let's see. Okay. So, any questions about? Okay. Actually, one more thing. And I also wrote down over here how you could work this out in terms of notation if you use the fundamental thermic calculus. So as we've seen, you can use either the plus C method or the FTC method. And of course, they both work because we're doing math. Okay. Let's see. Let me wrap up. Oh. Let's see. Actually, you know what? Let me talk about that next time. All right. So, any questions?
Attendance?
Okay.